Alright, so abstract classes are a class of classes, if you will. And then the non-abstract classes underneath it, in this case, are zero and successor. Alright. I'm not so clear on what function, what role public is serving here. We could try to pick up some sort of basic knowledge of the programming languages, but argument names such as in may occur in Lin's error messages. Let's see, in C# or Java, NAT could be defined as follows. Okay. Just as in the Boole example above, this defines more types than the Lean equivalent. Doesn't? It has more code. What? Yeah, I guess we would need to know what this is doing. Additionally, this example highlights how Lean data type constructors are much more like subclasses of an abstract class. Data type constructors. I want to cover that in a second. Are much more like subclasses of an abstract class than they are like constructors in C# or Java, as the constructor shown here contains initialization code to be executed, which I assume is this. Some types are also similar to using a string tag to encode discriminated unions in TypeScript. In TypeScript, NAT could be defined as follows. Discriminated unions. Oh, there's an F# mention over here. Discriminated unions, also known as tagged unions or variant records, are a type of data structure that holds a value that can be one of several different but fixed types. A type of data structure that holds a value, where the value can be one of several different but fixed types. They're used to represent values that can be one of a number of named cases, each with its own data and type. A key feature is the presence of a discriminator or tag that explicitly identifies which type is currently in use. Here's a more detailed explanation. Key concepts. Union of types. A discriminated union allows you to represent a type that can be one of several different types at different times. This is unlike a standard union where the underlying memory location is shared and the contents are potentially overwritten. Discriminator/tag. Each variant or case of the union includes a discriminator or tag, which is a field that identifies which variant is currently active. This field is typically a literal value, like a string or number, and can be used to determine the type. By using a discriminator, the type system can be used to enforce type safety and provide better tooling like auto-completion. Tooling. Exhaustive checking. In languages that support discriminated unions, you can often perform exhaustive checks on the discriminant to ensure that all possible cases are handled. In this example, the shape type is a discriminated union of square and rectangle. The kind property acts as the discriminator, if kind, allowing the code to correctly handle each shape type. Discriminated unions are a powerful tool for modeling data that can take all different forms, providing improved type safety, enhanced tooling, and increased code clarity and maintainability. Commonly used in languages like TypeScript, F#, and Rust. I see, so this explains what the author was saying earlier. Just like C# and Java, this encoding ends up with more types than lean, because 0 and successor are each a type of their own. Also, as opposed to lean, where nat encompasses both of these. Both of these are nats, whereas this nat is an abstract class. Though I was under the impression that this is also how we're using inductive. I was under the impression that inductive as a way of holding some types. Well, yeah, I guess I don't see the distinction here where we're saying the abstract class. Okay, so 0 and the successor are classes of the abstract class. Okay, so we're going to treat them as separate. Here, 0 and successor are components of a subtype, or rather component of a sum type. Okay, but they don't count as their own types. Yeah, this would be a mechanical question. I don't know if the distinction the author is making is worth making. Some types, no, let's see. Also illustrates that lean constructors, which are e.g. 0 and successor, correspond to objects in JavaScript or TypeScript that include a tag that identifies the contents. Okay. Pattern matching. In many languages, these kinds of data are consumed by first using an instance of operator to check which subclass has been received and reading the values of the fields that are available in the given subclass. The instance of check determines which code to run, ensuring that the data needed by this code is available, while the fields themselves provide the data. In Lean, both of these purposes are simultaneously served by pattern matching. An instance of operators, so we pattern match to determine which subclass has been received. And reading the fields that are available in the given subclass. In Lean, both of these purposes are simultaneously served by pattern matching. An example of a function that uses pattern matching is zero, which is a function that returns true when its argument is nat zero or false otherwise. Okay. Actually, let's take this back to yeah, so part of the idea behind, let me reiterate the idea here. Part of the idea that we're having here is, or from okay. Yesterday we arrived at the conclusion, had the idea that we should come up with a subset of racket that is more or less directly translatable. More or less, like, directly transliterable, word for word. I noticed they're, like let definitions, for instance. I guess most languages are going to have let definitions and they're going to work roughly the same way. But there's no sort of cognitive overhead, no cognitive load associated with replacing racket lets with lean lets. And lean is functional, purely functional, so something like tail recursion, which is already how I prefer to do code, works. Okay, now the idea is that we want to build out this subset of lean first, and then build off of it, build off this subset of lean as if we were learning new primitives in Racket. Okay, now what does that tell me here? Why is that relevant here? As if we are building off of this subset. Well, okay, I don't see quite why it's relevant, though there is a point here that then what we're mainly concerned with lean for now is understanding its type system and then understanding how its proof system works. So the proof system will be like a standalone language, as it were, that happens to use some of the same connective syntax. Okay, not quite relevant. Anyway, define is 0 in nat bool. Okay, match in with nat.0 true, nat.successor k false. If I can match in with 0, then is 0 is true. If I can instead match it with the successor, okay, I don't know, this seems strange to me. Maybe we need to seek some explanation of this. I mean, that our natural numbers are not going around stated in the form of a successor operation. I have 5. I literally do not have the successor of 4. I could replace all instances of 5 with successor of 4, according to Peano, but I don't. The match expression is provided by the function's argument in for destructuring. If in was constructed by nat0, then the first branch of the pattern match is taken, and the result is true. Alright, so this is what our interlocutor has been saying. This is our correlate to cond. Okay. Hopefully with will you look at that? I might want to do like that. It might not exactly be the correlate to cond. Well, so there's a point also that we might end up contorting language features because we want the language feature, and then we want to say like we want a language feature from racket into lean or lean into racket, and we say, well, really this is like cond. And then if it turns out it can work like cond, but that's not really what it is, then we would sort of twist it into position. I don't know if match is such a case. We can... So... Pattern matching. Match E ... with... Okay, matches each given term E against each pattern P of a match alternative. Okay. When all patterns of an alternative match... The match term evaluates to the value of the corresponding right-hand side of F, with the pattern variables bound to the respective matched values. If used as match HE with pipe P... Okay, I don't know what any of this is saying. When not constructing a proof, match does not automatically substitute variables matched on... When not constructing a proof, match does not automatically substitute variables matched on independent variables types. Okay. If in was constructed by nat0, the first branch of the pattern match is taken, and the result is true. So this matching would have to this matching would have to look at would have to look at the type of would have to look at this, would have to look at the constructor for in. Right. Let's see. Let's look at our most recent offer by the interlocutor. Let's see. No. The author offers this code. So we defined value to give ourselves the ability to form lists. Okay. We wanted to be able to form lists out of, in this case, nats, bools, and strings. Okay, so we made a sum type that had these three, and now I can have a list of values. Okay, where those are now all of the same type value. Okay. Extend our previous value type to include labels or type tags with the data. Alright, so this is nat to int val, bool to bool val, string to string val. Okay, and we have sort of these padding spaces. Give this some padding spaces. Alright. Tagged value label. We're gonna have to see the explanation for this. Label string, label string, label string. Let's see an explanation here. Now each variant includes a label string like age or enabled and a payload of a specific type. So label isn't baked in. I'm not sure what it means for these to have, or what it means for each of these variant types to have a label, a payload of a specific type, as opposed to merely having the payload of the specific type. So these are additional entry fields. And then these have the same name, which might be confusing in other, or might be strange in other cases, because we'd want to be able to refer to, regardless of which of these values we're talking about, we'd want to be able to talk about the label specifically. Let's see. So tagged value int val age 42. bool value subscribed true, and tagged value string value name Alice. Okay. With our tagged, let's see, with our label being whatever we should so choose, right? So in the construction of any of these, we would need to provide a label, fill the label field. Okay. Now this is definition for data row. Okay. Which is a list of tagged values, which has been assigned to tag value int val age 42, right? So now we have a list. It's interesting that we do not have to name the length of a list, as we would have to do with a vector. Now data row contains a structured mixture of labeled data. Interesting. Process with pattern matching. Here's a function that formats each entry. So def format tagged value to string. Alright, so this plus plus is an exemplification of operator overloading. Well, it would if it was only plus, I guess. It would be if it was only plus. Instead, this is plus plus. A plus plus B is the result of the concatenation of A and B, usually read append. The meaning of this notation is type dependent. Conventions for notations and identifiers. The recommended spelling of plus plus and identifiers is append. Okay. Let me do a little bit of testing here. Let's see. Now, so if I have the word append, that is not correct. Yeah, I'm trying to think whether we should take some practice doing easy's translations between Racket easy solutions and lean solutions, because this kind of, like, I want to, well, so this says you can replace this with append, but then you can't do it like the way you can't do it in the immediately obvious way. Yeah, like I'm lacking basic understanding of how these functions are composed, and we're able to engage in reasoning beyond our mechanical capacity, as it were. We've extended our grasp, but by how much? Let's see. The style lets you encode structured mixed type data in a type-safe way, preserve extra metadata like field names, types, or tags, and use pattern matching to access and process values cleanly. It's like a similar observation that think here. Right, well, I think that anything that we learn about the language is going to be solidified through use, but if what I'm learning is beyond my capacity to implement, which is just about everything still, right? So the idea would be, well, we could take a little bit and try to do lean racket, lean Lisp, LeetCode Solutions, lean scheme lean. Yeah, we're looking for one that doesn't require strings. Let's see. How would I solve this using only lists? Let's look at our restrictions. Quick, can I translate checklist? Okay. No set, vector set, or hash set operations. Only define cond if, let, lambda, and data operations. Okay, every loop is let loop. Okay. So I assume we could simply call back. Only nat, int, bool, list, and pair. No require beyond racket slash list and racket base. Okay, because anything in racket list presumably could be constructed using lists. Okay. I think we can do that. I have an idea. Lessons. Then lack. I think I do not limit my I thinks. I do not have enough facility in syntax yet. These lessons then lack the context and lack the mechanical lack any mechanical underpinning. I am not incorporating this much about types into. I'm not incorporating this syntax that encodes types into the circumstances where it is used to encode types. I am thinking we should try to solve a LeetCode problem, called a coding puzzle. saying that's not a word though. It's like as if spelling is a bludgeon that we use to make people who are bad at remembering spelling feel bad. Transliterable. If you have an adequate grounding in the application. Really, like affixes and suffixes on Greek and Latin templates, according to Greek and Latin templates, is effectively how English expands. If not so much now, certainly for large stretches of English, that's how English expanded. Some dock worker would come up with a new English word, and then some scholar would come up with new Latin extension. And those were effectively the two ways that the English language expanded. And now the spelling is set in stone by computers, so transliterable is not a word. So instead I have to adopt this awkward circumlocution of saying that we can transliterate. Oh well. The plan we discussed elsewhere is like this. When solving LeetCode puzzles, we will restrict ourselves to a subset of Lean that we can transliterate into Racket. I have a puzzle in mind. I have a puzzle. I have identified a puzzle we can work on. With this puzzle, I will construct a Racket solution. We can look at, we can work through the process of translation. Plus, let's make it idea. How do I open? Let me see here. My computer can't run the main website of OpenAI, so I have to go to these plain text versions. We had. It seems like there's more than one kind of canvas that you can have, because we had one that was like this, where you can write, and then yeah, there's a better one for coding. Let's see. Alright, let's solve a LeetCode problem. Shall we? We're not trying to pass the time limit, though if we happened to pass the time limit. Constant extra space. Okay, yeah, we can do that. This will be... Well, there is this solution. We're not going to do that. We're going to make a list, and then every time we run into a new number, we're going to scan the entire list to ask whether the new number is already in the list. Okay, which is not a good solution. Admittedly, but alright, so define single number, define duplicate, single number. Alright, we're gonna have nums. Okay. Define list cycle function. Define cycle function nums list integer. So nums. Yes, well, so this style of annotation which we could also do with, yeah, though that might not be the correct notation. Well, actually, so what we could do is code up without the type annotation, and then look at how the type annotation works in Lean, and then annotate afterward to give ourselves a template for what type annotation should look like in Racket. Commented type annotations. List cycle function nums list integer. It actually raises a point about exposure to comments. What do I mean? So if we're going to be applying comments systematically as part of a kind of I don't know what word you'd use here. When we design a translator, we will have restricted our code to a subset of Racket that can be translated into Lean. However, there is an additional component to this, which is that we have to have some system in place for encoding typing as required by Lean. Now, it could be like this, and then we would need to parse. I feel like that would be more difficult because we'd have to be able to split atoms. Oh no. I don't think we want to be splitting atoms. So instead we want something like this. But I don't know what like this needs to be exactly like yet. So, nums, I'll just do it like this and then we can change it over. So nums list integer, duplicate, or storage list. Storage A, storage B list. Okay. Now, so cond null nums list integer, then return. Do we want to do a warehouse system? I feel like that's going to get a little bit complicated. But maybe. Let me see. We found a relatively uncomplicated way of doing this horrible thing that I want to do. What is this horrible thing we want to do? So we want to take each element out of nums and ask whether it is already among the elements we have taken out of nums. Okay, so I cycle through storage A. I need to keep track of what elements I've already encountered. So I pull them out of storage A and put them into storage B. Okay. Now, the problem here is, what if that element was already in storage B? Now, if storage B is empty, that isn't a risk. That isn't a problem. But if storage B is not empty, okay, so that means that we need some sort of transfer system so that storage B is always empty. Something like this. Okay, so we're cycling, we take our next element out of nums. Yeah, but how can we ever ensure that how can we ever ensure we have solved this? I think there is a good solution to this. How can we ensure that the list that we're consing onto does not already contain the element that we're looking for? Well, so we could continue through to the end would be a point, but we would rather not do that, right? I mean, that if storage A had 10 elements in it, we could find the duplicate element as the third element there, and then, yeah, so it, like if we, let's see. So list 7, 9, yeah, sure, 10. So what time is it? Right. So now we're going to have okay, and oops, the number in question is 4. Okay, so now we're gonna have 1. Now we're gonna have 2, and now we're gonna have 3. Okay, and then we have found 4. Now, the question is, what do we do with these two lists? Now, an answer here would be we simply append. Easy game, but we don't want to be running so many spare appends. We'd rather accomplish this through a rotation. Let me open up. I might have saved my clever solution. I should have saved my clever solution. Well, we'd have to search, and there is no way to search. Uh, okay, let's see what this is doing. That's a lot of setting. It's also pre-systematization, and it's 100, and it's doped. Oh no. Oh no, I did list doping. Why would you do that? It's subcond. Alright. Supposing I came up with a good solution for it, it is now buried. Alright. Okay, so now we have to suppose that we had an additional list, a list C. That's our sort of baseline out. It might turn out that it's not actually an out. We'll have to find out. We'll have to find out. Yes. Okay. Now there are three cases, or there are these cases. Case 1, A, B, C. Next number is in A. Case 2, next number is in B. So let's say case 1. So we're looking for, let's say 8. Let's say 7. Okay. And now again, the idea is that we have to be putting into an empty list, because if it turned out that the 7 was here, we don't want to have to recycle through the elements we've just looked at. So 5. I'll do 5. So we'll just say A was the default, which is reasonable. Yeah, let's just get rid of these. Alright, and now 6. And now, how did I... Alright. And now we have this additional list. So what this suggests, I think, is that we have a warehouse, which is why we call this warehouse sort, or warehouse, I don't know what we call it exactly, but alright, so we have, let's start back at the beginning. And we have a temporary container. Alright. And then we have, oh, and so that'll go here. Okay, and now we will have 3, 2, 1 here. 4 will be gone. We'll do that. Okay, and then okay, and now alright, and then we say we need 2. Okay. Or we can, let's do 7 again. So we'll say we're looking for 7. Okay. And now we will have, so we'll do dot 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 again. And now this will be 6, 5. And then these will delete. Okay. put that into storage. Alright. And now we are looking for 2. Okay. How unfortunate. Yeah. So we're going to do dot dot dot. And now we're going to have 2 empty 1098. 6, 5, 3, 2, 1. Okay. And now the next step here is to take out the 6. This list. Alright, and then it'll be dot dot dot. Okay, and now we will have 2 empty 5, 6, 10, 9, 8, and 3, 2, 1. Okay, and then we illustrate this process again. Alright, and then we will have 2, 2, 1, 3, 5, 6, 10, 9, 8. Alright. And then delete. And this system works. Is it efficient? Compared to what? I guess that depends on how expensive list operations are. Who's asking? Alright, well, let's implement the solution. What happens if I type canvas? What happens if I type canvas? What happens if I do this? Canvas. Alright. First, I have an ASCII art style, as it were, for constructing examples and explanations for myself. If I paste my explanation into the algorithm we are implementing into the canvas, will we be able to read it as a... We have pasted if I paste my explanation for the algorithm where, if I paste my explanation, my accounting for the solution into the canvas, will you be able to read it as an example, as an explanation? To be clear, paste first the ragged code, but a stylized display of working, stylized working out. Let's remove this dot dot dot. This will be 4, or at least do 1 or 2 cycles. So the first time I used this, the interlocutor did not see what I put into the canvas, so I'm now wary. I don't want to confuse the interlocutor by speaking as if there's a solution when the interlocutor can't see the solution or the example. This is, nevertheless, we proceed. Let's see, this is a stylized, this is a working through of what we call the warehouse algorithm. I don't know if this is a algorithm, if this is a good enough to be recognized. I don't know if this algorithm is good enough to justify the position of books, justify the name, works like this. The problem we are solving. Given a non-empty array of integers nums, every element appears twice except for one. Find that single one. We're going to accomplish this as described as follows. I cycle through, I take an element out of a provided list. So actually what this is detailing is that this is all, these are pre-scanned. These must have been pre-scanned. These must already have been scanned. Alright, so I take an element out of a provided list. This element tells me what we are looking for. Tells me what number we are looking for our warehouse. Take an element out of a provided list. This element tells me what number we are looking for in our warehouse. On line 1 we have number. On line 1 we have the number we are searching for. On line 2 we have a list of elements we have already scanned. Ordering is coincidental. Each element we scan, we place. Place each element we scan into a temporary box, temporary list. If we either run through the entire source list, we place each element. Now maybe I'm realizing I don't have such a firm grasp on what this is it's talking about. We place each element we scan into a temporary list. When we find an element we are looking for, that temporary list always goes into the warehouse, indicating Right, so each line with open parent, or yeah, the blank parent or in represents the target number being searched. The list below it is the current stream of candidates being scanned. The second list accumulates already seen items. Once an entire search fails, no match found, the second list is deposited into a warehouse. The warehouse is later dequeued into the scanning stream for another pass, restarting the search. Okay. So yeah, so if the entire search could fail, we would deposit the box into the warehouse. I guess we're trusting the data source that an entire search can't fail. This results in a layered unfolding algorithm that ultimately isolates the unique element by elimination, with each layer of the warehouse representing a level of duplicated failure. Interpretive summary of what you're doing. Start with a target value and a stream of remaining values. Try to find the matching value in the stream. If found, discard both and do not warehouse the current accumulation. Let me see. Okay. Yeah, I see what this is saying. Try to find the matching value in the stream. Do not warehouse the current accumulation. So if this is using the word accumulator correctly, I think this description's a little bit wrong. Let me see here. Try to find the matching. So start with a target value and a stream of remaining values. So we have our target value and we have our stream of remaining values. Alright, if found, discard both. Do not warehouse the current accumulation. No, I think that is a mischaracterization, because here in the step from yes, here in the step from, so we eliminate 4, and then we take this step between 26 and 29 to 31 to 33 to put this list into the warehouse. And then yeah, maybe I shouldn't have done the dot dot dots. Oh well, let's see. If not found, place the accumulation into the warehouse. Once the stream is exhausted, pull a new list from the warehouse and resume searching. So that characterization doesn't work, because if I place, this would go into an infinite loop, where if I place the accumulated list into the warehouse, we would then pull it back out from the warehouse, cycle through it again, put it back in the warehouse. The unique number will eventually remain as a single unmatched element. That is true. Let's see. adjust the numbering scheme. Well, you just burnt entire solar panels worth of electricity for today, but whatever. Let's see. So, let's see. Yeah, I'll go ahead and implement, and then we'll offer the updated explanation alongside the implementation. All right, so we have. Let me see here. Yeah, how this gets started, I'm not sure. Temporary list. Let me think here. So we pass in nums. Storage list integer starts empty. And this can be nat, I assume. No, as it turns out, it has to be an integer. That's unfortunate. I mean, we could do nat and just only do positive examples, but okay. Let's see what we can work with here. So we got storage list, and then we have temporary list integer, and then we have warehouse list integer. Okay, so now null nums list integer. Actually, so we wouldn't have a temporary list here. So this is actually, we can call this num cycle. Okay, and now null nums list integer, then I don't know what we would do in that case. Else pass to storage cycle function with cdr nums list integer car nums list integer storage. Actually, I could put that at the bottom maybe. Storage list integer temporary list integer warehouse list integer and car nums list integer. Okay, find storage cycle function with nums list integer. Let's see, yeah, all of this could be the same except for car. So this would be search or target integer. And inventory. What would be a typical warehouse word for a singular object? Let's see if Google has an idea for that. Typical word for a singular object like warehouse. A single object in a warehouse can be referred to as a stock keeping unit. Okay, we'll do SKU then. Okay. Keep this, yeah, box is a type in Racket. We could name this like withdrawal box and deposit box. And now temporary list. Now, cont null withdraw box list integer, then run storage cycle function with let's see, now this will be car of if null warehouse who knows? Otherwise, storage cycle function. I gotta exercise soon. Yeah, I gotta exercise earlier actually. This will be car. Okay, this will be CDR. Let active integer car withdraw box list integer. Let's say comparison integer. Car withdraw box list integer. Alright, and now we're gonna say equals comparison integer SKU integer, then go back to num cycle so withdraw box stays. That'd be CDR withdraw box. CDR withdraw box. And then const. Okay. Otherwise, storage cycle function with Alright, so that's probably it. I'll submit this and see if it works. Well, no, I mean, we have to fill in the parents. Yeah, alright. We might only do one exercise cycle. My upper body is out of sorts after yesterday. Yeah, I'll be right back. Standing up. Oof. Oh. this. Should do all of this code in a breakout object-oriented racket and just completely defy the whole point of the exercise. Yeah. Let's see. I don't know how to write object-oriented racket. I wouldn't be able to follow through on that joke even if I wanted to. We might continue this project over to, well, I don't know, we'll see what the today's medium problem looks like. If it looks solvable quickly. Okay. Now what? Alright, so what do we do in the null cases? So this would be SKU integer. Okay, so actually it looks like we don't need this function at all. Right, maybe just call back to storage cycle. Okay, withdraw. Let's see, CDR withdraw box, list integer, null, and then const deposit box list integer onto warehouse list integer and car list integer. Okay. Yeah, it does seem like a problem, doesn't it? Hold on. I might be leading us into a folie à deux. How does this actually work? No, yeah, we do need a null nums. I think. I didn't expect this to require as much thinking power. Let's see. So I think this is if null nums list integer, then SKU integer, otherwise storage cycle. With so this goes back to null. This is const this SKU integer onto deposit box list integer onto warehouse list integer. This will be car list integer. This will be CDR. And this will be withdrawal box. No, null withdrawal box. Oh, wait, hold on. So then, yes, car warehouse list. Okay, then we could just do. Right, we could do. Alright, so this is a little bit concerning, but it's not illegal. Not illegal, yeah. Let's see. If null withdrawal box, so we've cycled through all of the withdrawal box. Okay, which incidentally starts out as null. So we would immediately trip this, then we ask if warehouse is null. That is also true because the warehouse starts as null. Is the nums list integer null? If so, then there was only a singular element in the list. So we return that element. Otherwise, we const SKU integer onto deposit box list integer, which is null, producing a list with only that singular element at the moment. And we put that into the withdrawal box and cycle back. We put car of nums into the SKU position, and we return CDR nums list as nums list. Okay. And then now we have the first element in the list. Withdrawal box is not null. Comparison integer is car equals comparison integer SKU. SKU, no, probably not. Alright, then we go down here. Storage cycle function. Okay. We CDR the withdrawal box, we const the comparison integer onto deposit box. Warehouse remains unchanged. When we come back later, or in the next step, well, actually in the next steps, withdrawal box would be empty. Alright, so then we cycle through. Is the warehouse null? Yes. Is nums null? No. Actually, conveniently, we can replace this with a literal. Okay. Eventually we hit an equality. So notably we now have, we const the new SKU onto the deposit box. That contained the first element, now it contains the second, then the first element. Alright, so we extract a comparison integer from the withdrawal box. Equals comparison integer, SKU integer. If this ever becomes true, then CDR withdrawal box. Okay, Okay, we const the deposit box into the warehouse, and we take the new card nums. That's where we get our first list that's in the warehouse, our first box in the warehouse. Okay. Now later, null withdrawal box, null warehouse will be false. Then in such a case, we take CDR of warehouse and put that element into the withdrawal box position, keeping the deposit box. Okay. Alright, let's see if it works. Let's run it. Oh, we have to fill out this form. Null withdrawal box, null deposit box, null warehouse, and car nums. Alright. I didn't even check for static. No static. Runtime error. Expected pair given null. Huh. Let's see. 41212. Huh. I guess we supposed we had some kind of protection against this baked into the other checks we were performing. Either that or we supposed nothing. I guess, well, this is why we initially had a separate function specifically asking null checks for this, but how do we get around this? So actually, this might present an interesting case. We don't know anything about how lean proofs work, but this might present an interesting case for lean proofs because we need to show that every duplicate element gets caught. Alright, yeah, I have to do more working out of this example for myself before we can subject the interlocutor to it. Let's see. If null withdraw box well, show me, let's see.
So 4 goes into the withdrawal box, and it gets placed into the deposit box, and then we put the withdrawal box back up. 1 gets put into the withdrawal box as well, then 1 into deposit. Skew is 2, 1 into deposit, 4 into deposit, no match for 2. Now skew is back to 1. We have 4, 1, 2 in the deposit box, SKU of 1, skew of 1. Cycle through, 4, 2, and then we have 1 and 1. Now we have this in the warehouse. Hold on, but we can have... Yeah, but we don't know that the withdrawal box is empty. Alright, okay. It won't always be empty. Now we put 4 and 2 back up here. Alright, so in the preceding loop, we had... Well, no, this is the current loop. Right, why didn't we display nums? Alright, so now we have nums, which is empty. Okay, so we can restructure this as a cond. Not equals. Then okay. Null nums list integer. Then I don't know yet. Else. Alright, so what do we do if nums null list integer? I think we could have chosen a better example. It's unfortunate that we're going to have this horrible sequence of ifs at the top. And then we're going to have, this is going to be like a nested cond, I guess. Let's see. So the idea is that in this, the last state, we want to pass forward the deposit box and the warehouse. Okay, and then define warehouse search function, deposit box list integer, list integer. Alright, cond null deposit box list integer. Then I guess in this new era of safe coding, we should say if null deposit box integer, if null warehouse list integer, oops, otherwise, call warehouse search function with car warehouse list integer, CR deposit box list integer. Okay. Otherwise, warehouse search function with deposit CDR deposit box list. Oh, so yeah, here we need. Well, there's only a singular element. Oh, right. So if not null deposit box, then car deposit box list integer. Okay. All right, there's our code, such as it is. Let's see. Curses. All right. Oops, rather CDR warehouse. Alright. Uh-huh. Uh-huh. Is this gonna crash my computer if I try to paste it? Because it might. Let me see here. Why would this fail? Comma deleter. I guess we'll want to save this. This is not the formatting I want to have. No, hold on. Out, no. No, this is not it. This is horrible. Hold on. I don't know where this folder is either, so it might be here or it might not be. I don't know. Users? I don't know. Alright, the answer is no, I guess. Let's see, can we get a different view? List, is that maybe what we wanted? Hold on. I use search and everything breaks. I don't want search results though, is the thing. Nor do I want to go to an entirely new folder. What Windows, why are you doing this to me? Is it an E? Is that where I put racket? Maybe. Yeah, I have no idea how to navigate my own computer. And that's because navigation has always been horrible, so I've been restricted to a small enclosure of my computer, I would say, is the reason. It's because if you try to move around in the computer, you get an electric shock, and then you get told to go back into the pin. You say, okay, I'll go back over there. Let's see. Users, reader, documents. Why would it? There's never a good answer to the question why, would, etc. Okay, we found it. And now I'm going to put in warehouse algorithm. Oh, okay. Now that we have warehouse algorithm save, warehouse notes. Alright, now what? so now we want to find comma deleter. It might not still be in. Oh boy. Oh boy, we get to use search again. Nope, there it is. Alright. Now the question, is this going to crash my computer? We need to design another comma delete, I think, probably, because this has doping, and we don't really need doping, do we? Okay. Okay. Now I will copy this thing and hope that my computer doesn't crash. Though it might. Or we reason about the case and try to figure out why this would fail. Which we would do after lunch anyway. Okay. Storage cycle function. we said one exercise segment. And I started out too late. Also, I'm gonna end up exercising pretty hard for our model theory segment, so I think I'll just call it for lunch here. I'll be back for... Yeah, well, we'll look at the medium LeetCode problem, the daily, and then if we can solve it fast, we'll switch over to resolving this problem. Alternatively, depending on my preference, we might simply stick to this so that we can get in some of the putative learning lean, the purported learning of lean today. So we're going to translate this into non-idiomatic lean ward. Our interlocutor used that word. Seems like a good name. Lean ward. Anyway, be back soon.